G'day everybody, and again welcome back to the channel. I'd just like to ask you guys again one more time just to give some feedback on my new video angle. So like when I move my head in to try and get close, is it better and off camera now? I think it is. I'm not too sure. It should be at least better. And as I showed in the last video, that I've got different angles. You know, I can look that way, I can look this way, I can look straight down. My apologies about that. I hit stop moving the phone. I can move the phone quite a bit each way also. So I just think this is a better setup. So leave it in the comment section what you think. Anyway, without further ado, let's get on with the video. Now, I know this is an unrelated subject, but I just want to touch on it because I think I'm a genius. I was doing research into Johnson current noise on resistors, which is why I've got metal film and carbon film resistors. And I thought that some of the choices I might have made were wrong. Turns out I was literally more correct than you could be. So the higher the resistance on a carbon film resistor, due to the carbon molecules being all random, the way it's composed, it creates noise as the electrons pass. But the higher the resistance, the more noise there is, but also the higher the current, the more noise there is. So the point I'm getting at is if you've got a low resistor value with only a few milliamps going through it, you're not going to get noise. You got a low resistor value with amps going through it, you're going to get noise. You got a higher resistor value with milliamps going through it, you're going to get noise. I hope that makes sense. And if you got a high value with amps, you're going to get a shit ton of noise. But you get what I'm saying. So where my collector and emitter resistors are on the input, they're carbon film, but they're low value. You know, 47, 68 ohms. And you got a couple of milliamps going through each one at the most. The higher resistance, 2K2, it's metal film. And then where I had to use two resistors to build the sort of bootstrapped current source thing, two 5.6Ks, I used one metal film and one carbon film, and I put the metal film one to the side that goes to the base of the transistor because it's going to have less noise, and the carbon film one on the other side. The reason I didn't use two metal film ones is because I'm trying to minimize inductance as well. So the whole thing with the, as I've said before, with the resistors in this is noise, inductance. And so basically every resistor location I choose what, yeah, I think I've said enough. Anyway, on with this. What I have here is a rail that's referenced to the negative rail that we can, let me just make sure I set this up right. Yeah, which can go below the negative rail. Currently it's 3 volts below the negative rail. It's not turned on, but it's got to hit a button. I'm going to try that first, obviously, before the bootstrap diodes. But before I turn that and do that, I'm just going to add some more capacitance across the millicaps. Now, the other thing I've done, like I said, I am going to put a current source on the beta enhanced transistor, and we're going to have a regulated rail for both these transistors, so they'll be isolated in terms of noise rejection. But I was thinking about that ground wire. You know how I had these little ground wires from there to there and from there to there? I removed them and changed them for a single ground wire, and then I put them back. Well, I went back to this way, and here's why. I was thinking about it. Whilst it might not affect the DC characteristics of the amp, it will affect THD and linearity, because those that's a current source, that's a current source, and that's the collector of the beta enhanced transistor. This is feeding that. If this has got current pulses, i.e. its voltage is going up and down on it because it's got other ground currents passing through the same loop, those current sources will have varying voltages on the tailwind, and the collector voltage on this transistor will be modulating. So I went back and put an extra ground wire. I mean, look, I put, literally dual wires for drivers and outputs, right? I've got dual ground rails. This is just for capacitive decoupling. These two are just for DC grounding. And then these other two green wires are for audio ground for each channel. So it's completely split up. And so I've gone back to that. I've also added the 100 ohm resistor to the collector of the 3200 transistor, the beta enhanced transistor. I've also put the 3200 in the other side as well because it's a definite thing I'm going to do, so I figured I might as well do it. But that's neither here nor there because I'm going to disconnect that side so it's not powered up. But yeah, I just sort of point all that out. The 100 ohm resistor is only temporary. It's just when I designed this, I had it in there, so I've just put it back. It's just going to help with high frequency stability. 100 ohms isn't going to get into Miller area. I think around above that towards 1K would, but 100 ohms will be fine. That's only temporary because it's going to be replaced with a current source, but I still want it there instead of nothing there whilst we're trying to solve this problem. So I hope I've explained everything and that makes sense. What I'm going to do now is I'm going to isolate the other half of the amp. So I've got no power to the Vasen driver. Got power to my output stage. However, I can just remove its drive just in case there's some stored charge in here or something, and the transistors aren't fully turned off. If they've got nothing on their bases, it's high gain, but it's still not high enough for them to just turn on from the bases being floating. So I'll just leave the bases on that channel floating. And no power to that driver board. That way we've only got the one channel and one driver board, because it's just going to be a lot easier to work on one thing at a time. Also, originally I found it was even oscillating worse with both hooked up at the same time. Although, like I said before in the last video, I want to design an amp to be as stable as it can be with the worst conditions and minimal compensation. So I want, best slew rate, best frequency response, best THD, best noise rejection with minimal compensation, and I want it to be stable under a lot of conditions, including load. Like that's the reason why I've got all these current sources, the beta enhanced VAS, the triple Darlington output stage especially, because I want this to be load invariant basically, and it will be. So yeah, there's a lot going into this in terms of thought process, but yeah. What I'm going to do now is I'm going to lift this 68 ohm resistor from the VAS transistor. I'm going to just do some research and see. I'm going to do some thinking first, and if I can't work it out myself, I'll do some research. I think I want to lift the emitter resistor from the beta enhanced transistor as well, and the emitter resistor from the VAS transistor, and run them both from a sub rail. Because the way I see it is this transistor is driving this transistor. If this transistor's rail's now a little bit lower, wouldn't this transistor need to be able to go that much lower to drive? You know what I'm saying? Well, let me think about this for a second. This transistor turns on, turns that on. Yeah, they both have to go from the same rail. I'm going to do some thinking and I'll be back. Alright, so I was a little confused having a look at the Baker clamp diodes people were using, because some people were using Schottkys, some people were using like 4148s. It turns out some people have got a single VAS, some have got a dual stage VAS, and some people are trying to make up an extra diode volt drop in the bait. It's a long story, but anyway, the diode I need to use is, I don't think it's a Schottky. Oh my god, I just got the data sheet. I'm a little bit confused on one thing, so I'll put the data sheet on my computer and I'll show you, because I'll just show you. Alright, so this is what I'm a bit confused about. Everyone says that it's faster. Less than 2 picofarads capacitance, right? Reverse recovery time 50 nanoseconds. VAS 16. 1.5 picofarads, 6 nanoseconds. So straight off the bat, you think that that's faster. But what I think's going on here, so that says ultra fast switching speed, less than 4 nanoseconds. And it says max 6 there. This says forward current 10 milliamps to, what's that, reverse current 1 milliamp. What's R? Must be reverse. Anyway, reverse voltage 6 volts. This was measured from 30 milliamps forward to 30 milliamps reverse, 100 ohms, measured at reverse current of 3 milliamps. What? Yeah, it makes no sense to me. I'm really having a hard time working that out. Yeah, I'm confused. I hope I haven't just ordered the wrong diode, but I've been Googling and looking on forums and everyone says this is faster, so it must be, I'm not good at math, as you guys know. It must be something to do with these specs. Like what I'm saying is, if you stretched out the numbers here to measure this diode, this would probably drop down below the other one. That's what I'm guessing. I'm really confused over this. If anyone out there understands, I'm really not good in the time domain and maths. So if you could help me understand the measurement difference here, and why this looks like it's faster than this, but this is supposed to be the fastest part. So even here it says high switching speed, less than 50 nanoseconds. This one, it says less than, it says ultra fast switching speed. I'm starting to think I'm right and everyone else is wrong. And I mean, yeah, I get the current difference, but it's not that much of a difference for the speed difference. And when they advertise at the top of the page stuff like ultra fast or just fast or very fast, it's the same as diodes. You know, you get like normal signal, ultra fast, super fast. You know what I mean? And they'll have a different meaning. They are faster. So, yeah, if anyone can help me here, please help. Obviously, I'm going to keep researching this. But at the moment, I am quite confused, and I don't see why reverse voltage is going to be a problem. The non-repetitive peak reverse voltage is 100 volts for the 16, and the repetitive or even working peak reverse voltage, DC blocking voltage, it's 75 volts. There's only 63 volt rails, and we're only looking at the swing that's there between those transistors, which is not much. So I don't know. I am a little confused. I'll go do a little bit more research, see if I can dig anything up. The problem is I'm uploading a video to YouTube right now, and my internet bandwidth, when I'm uploading something, I cannot use my internet. When I'm downloading, it's fine, but my upload speed sucks, and then for some reason my download speed gets swamped when it's uploading. I guess it's because it's wireless. If it was wired, which I keep saying I'm going to get around to doing it, I'm still wasting money like this, so I've got to get off my ass and do it. But I've just had so many other bills and things that I've been trying to pay whilst buying components and stuff for my hobby, and those two things are always fighting over each other, so I seem to never get other stuff done. But we'll get there. I'm going to go try and work out this diode situation, because yeah, I'm bloody confused. I might be officially losing my mind more. Hooked the multimeter up to the ground rail, positive to the output of the amplifier, right? Now, I don't know if I've got something worked out wrong in my head here, but if the VAS transistor, which is on the bottom PNP side, was saturated, turned on, it would be sinking current out of the PNP driver, turning the PNP side on. It would be stuck to the negative rail. I don't know if I've got something backwards here, but I would think that would be what's happening. However, look at this. That's both sides stuck on. Alright, that's why the offset was 0, but it was drawing like an amp of current. Both sides are turned on. If I open up the bias spreader, stuck to the positive rail, which kind of makes sense because that's passing current from the current source down to the VAS transistor. Which is at the bottom. And I guess if the bias spreader is open, all the current source current goes in the NPN transistor, and none of it goes through the bias spreader into the PNP transistor to compensate the negative voltage there, and into the collector of the VAS. So I'm confused now. I can tell you one thing, this getting hot, this 2K2 resistor, indicating this is hard turned on, it explains what's going on. It's sticking at the positive rail, and the VAS is actually trying to bring it back down to the negative rail. Now, here's where I'm even more confused. Why is it sticking to the positive rail? Has everything I've just researched about the VAS turned out to be useless, and the problem's not my VAS? I am even more confused. One good thing is I did some research from some actual like trusted sources, papers from companies and stuff like that. The BAS21J is faster. Its typical capacitance is 0.3 picofarads. And it's got a higher reverse voltage and a couple other things that math out to make it a faster diode. So I did order the correct diode, thank goodness. BAS21S, BAS21's also good too, but BAS21J is the best, so that's the one I ordered. They cost $3.11 or something for 50 of them, $6 something to get 50 delivered to my house, so can't complain. And no, they're not like Chinese copies or something. I've gotten them from one of my reputable sellers where all these good, nice parts come from. So I'm going to go do some research quickly, see if there's some other phenomena that exists with this amp that causes positive rail sticking, or am I just a dummy and it is the VAS and I'm just not getting what's going on. I don't know, like, is it somehow not turning on enough to pull it back down, which I don't understand how that's even possible. Yeah, I've got a few questions, but I'm gonna go do a bit more research and then come back and then we'll continue looking at this. So other than a drive issue, the only other thing I could see that would stop the VAS transistor in saturation from not being able to get it away from the positive rail would be if its saturation voltage is too high in combination with the voltage drop on the emitter resistor. So let's how can I get you a better view? Let's have a look at the saturation at 10 milliamps because that's roughly where it's being run at. What's the pin out on this guy? It's base collector emitter. And it's a PNP. VC sat 10 milliamps. Base current 10 milliamps. Collector current's what we want. Oh, that's HFE. I was going to say what? Excuse me? Oh, dude, it's an NPN. What am I saying? Yeah, even at 100 milliamps, it's nothing. So it's not saturation voltage being too high, and I have shorted over that resistor, so I know it's not that. So at least that's that ruled out. I just had another thought. Maybe when the VAS transistor saturates, it's not able enough to source enough current, you know, from the current. Oh no, it's coming straight off the rail. What am I saying? I was thinking maybe somehow it ends up outside, it ends up running an open loop, and then can't recover. But yeah, that doesn't really make sense either, because that would be the opposite. I am bloody confused. Alright, so I'm finally working back in here on this. And I was just watching over the earlier portion of the video and something came to my attention. Well, a couple of things. Firstly, I said bootstrapped current source and then bootstrapped diode. Yeah, I don't even know what I was talking about there. The current source is filtered. the reference, not bootstrapped. And the diode that I was referring to, it's not a bootstrap diode, it's a Baker clamp. So anyway, second thing, maybe I was asleep that day. I was also saying, am I going to lift the emitter of the driver transistor, beta enhance, and the VAS transistor and run them from a sub-rail? Why on earth did I even need to think about that? Of course it's only the VAS transistor, because the reason we're doing that is to stop it from going into saturation by making its emitter a bit lower than the transistor that's driving it, so that the transistor that drives it can't saturate it. I must have been really asleep that day. Anyway, with those things out of the way, let's continue. Alright, so I've left another note for myself, because I was thinking about it further, and depending whether I want to stop the VAS transistor from being saturated or I want it to be able to drive down lower, well, with those two options, one of them I'm going to want its emitter from a lower rail. With the other option, I'm going to want both those transistors, the beta enhanced transistor and the VAS transistor's emitter, from a lower rail. Also, I was thinking, is it something to do with the input stage not having sufficient drive to drive the VAS stage? So I've got a couple of things to investigate. I'm going to go do a little bit more reading on the subject, because I don't want to waste too much time, but if I can't turn anything up, I guess we will just look at what I've been talking about. Alright, I'm finally back to work in the lab. As it's been a few days, more than a few days to be honest, since I've worked on the actual amplifier build itself, I'm getting a bit rusty. That's what happens. Those of you that design stuff, you know what it's like. Especially when you're like me, you don't use sim software, you draw schematics after you've designed your work, usually on breadboard and then sort of on PCB, and then when you're happy with it, you start making schematics or half schematics as you go. And if you stop something like that halfway through and then come back to it a week or whatever later, it can be really hard to remember exactly what you did or what you were up to. I'll give you a bit of an example. I can see here, I can tell I've got these two LEDs here because I want to better couple that LED to that transistor, so I know that. And I can see here I've got my two 5.6K resistors and everything here to set up a current source. But is that just in case that worked for the other one? And if it is, then why do I have two in a bag up here? Because over here I've got all the upgrades that I've so far added to the other board. So the two little riser boards, the changes on the power resistors, the pots and the bias resistors, everything I've decided is definite is in this bag over here for this board. So I'm already looking at my bench going, what? And this is just after what, 9 days or something. I don't know. It's not too long, but yeah, so anyway, I have done some thinking. I watched the last video I uploaded, and I just need to point something out. I'm sorry if I confused anyone in that video. I said so many things, like I did earlier in this video, that just didn't make sense. I don't know. I was having a few bad brain days. I don't know what to make of it. I mean, I was missing sleep, but yeah. My sleep patterns, they get thrown out really easy. I start working later and later through the night, and then waking up later during the day, and then I see that happening and I try and get myself back, and it's just a vicious cycle. I'm always getting better and getting worse, and when I'm in between those two spots, I'm not doing good. Anyway, I think that's what happened. But I said some stuff that didn't even make sense to me, and I was just like, wow, okay. Anyway, moving on. I watched that. I watched the earlier segments of this video that I've recorded. And as you know, yesterday I've come in here and laid some notes down just to point some things out. And whilst that's all fresh in my memory, what I've just seen, I've got a good idea of where I'm up to. I started thinking about the Baker clamp diode. Oh, and one other thing I need to bring your attention to also is I've got a lot of stuff on my computer screen. Now, again, I know I showed a lot of this in the last video, but I remember I was trying to find reference. Remember I was talking about, I found someone that suggested running the VAS rail a few volts lower than the negative rail, which is what this is here for. Well, I still couldn't find the exact article. But what I did find was this. And it's someone saying, well, what I like about this is it covers two things that I'm concerned about. I don't want to use a Baker clamp, and here's why. I'll pull up Spice and just show you just someone else's implementation, but I'm pretty sure the Baker clamp actually is supposed to go from here to here. It essentially goes across these two capacitors. So let me just, is there one on here? No. Let's have a look at some other people's designs that I've still left all this stuff up. Oh man. I know. Here we go. Right, so we've got our drive transistor and our VAS transistor, and as you can see, the Baker clamp goes from the base to the collector, like I said. So that's how we're going to be implementing it. Now, if we do that, if you think about it, it's a little bit much. Having, especially not a full 148, but a Schottky that's, I don't know, 200, 300, 400 millivolt forward voltage across here, it's, you know, all that gain and work these two transistors can do, boosting voltage, is essentially like fed forward on the positive half via the diode, you know. I'm not too sure how that works. I mean, the transistors are still going to work, but they're not going to be able to saturate. But the way I see it is the lower the voltage of the diode, the less the transistors are going to be able to work at all. But the problem is if you go with a high voltage diode, you've got a higher capacitance there, and then you run into bandwidth problems. So, where am I found this. Yes, there are two easy tricks. Divide supply into two different levels and use the input stage plus VAS supply as a possible higher than output stage. That's basically what I was saying about bringing the VAS rail lower. So I've now found a second reference to that, which is good. Now, I showed all of this stuff in earlier videos, or the last video, you know, and the BAS21J, it seems like it will do a good job, all right, but, you know, and as you can see here, again, in a lot of amp designs, it's used. This is complementary VAS, so there's two, but like I said, it's going to have a really big effect on the feedback response, and I don't want to do that. So we'll try other fixes first. Now, something else I've got here ready, this has got nothing to do with what I'm doing now, but a guy on DIY audio forums, PMA, he and Bonsai and a few other users on there, they are what I consider at least above my level or at my level. They know what they're really doing. They, sorry about the focus, I just realized what was going on there. They know what they're doing, all right? And he's designed a dummy load to mimic a speaker, which is really cool. And he's also designed a torture test load. So I thought those were some nice little circuits to take a look at. Obviously, it's got nothing to do with what we're doing now, like I said. But I just wanted to give you guys a look at that. Food for thought, something that will be coming up. All right, so what I've got is I've got my bases isolated to the left channel, the resistors that power the left channel rails. Driver stage is still powered, just not the input stage and VAS. All right, so I should be able to power this up now, and I've just got this one channel connected as it originally was. At the moment, everything's still connected to the best of my ability. It looks like everything is where it's supposed to be. So I'm just going to get my multimeter, because it's literally been days. I don't even know what this is doing. I need to look at it. I know it's rail sticking and all that, but I mean, let's just see what is going on. Okay, that won't start up at all. At all. It's interesting. I really don't recall it being this much of a problem. Well, that time it started up. Okay, there you go. It's just that bloody offset rail sticking problem. It's unstable. Like I said, it works. As you know, it's just on the edge of stability. If I just touch that input capital, yeah, you hear those relays clip. It swings to the rails, clips. Usually it comes out of clipping, but there you go. It's taking 1.1 amps now. Just recover it. And that's interesting, because you know what I just noticed then? When it drew that extra current, it didn't go to the rail. Oh, I wish I had noticed that before. You know what that is? That's both sides turning on at the same time. That's indicative of some sort of oscillation. Hold up. I might have accidentally just discovered something. Let me just work out a viable ground. Get this on times 10. Because capacitive loading on this is going to really muck with it. This is interesting. We might have discovered something. Because I've been thinking the whole time, there's something I'm missing. It just, like I said, I can't understand. If the VAS transistor was saturated, it would either be I would think if the VAS transistor was saturated, it would be sinking all the current out the PNP side, and it would be stuck to the negative rail. But I also get that if it's stuck at the positive rail, the VAS transistor could be saturating, trying to pull it to the negative, and then it's just turning both sides on. I think that's what's actually happening. Question is, why is it as soon as it goes to clip to a rail, it gets stuck there? Is it really? Or is it really somehow sticking to both the rails? Obviously, it's just spread out a little bit more than your average bias. It's about 1.1 amps it draws. It's not fully turning both sides on, which is why I'm starting to think it's oscillation. It's just impossible to probe this circuit. And, not, laid down the amp. I mean, there's noise there, but here's the thing. These are run straight off the rails. You've got your input stage, and oh my God, the noise gets bigger when I bring my hand to it. I mean, I can see that's literally just amplified noise. I'll show you guys. So that's the base of the beta enhanced transistor, and this is me moving my hand closer to the input cap. Oops. That's what I mean about unstable. So that's just amplifying noise. 500 kilohertz of it, at least. Alright, let's have a look at the output. It's interesting that at all these different nodes, i.e. the base of the beta enhanced transistor, the emitter of it, the base of the second one, it causes just as much instability. You'd think, you know, touching, say, that wire would cause a lot of instability because there's more gain there because it's on the base of the beta enhanced transistor, and say touching the second base wouldn't have as much of an effect, but it's just as unstable. It's amazing. Again, no signs of any sort of oscillation. It's just noise, gets louder when I bring my hand up to it, you know. Nothing that suggests anything is wrong there. I mean, the amp's not biased, by the way. But anyway, that's neither here nor there. It's not, that doesn't mean it can't work. It's just got crossover distortion. It's still going to amplify. So I am literally at a loss right now, because every time I think that I've come up with a solution, I think about it and I'm like, yeah, no. You know what I mean? We could just go trying stuff. I'm thinking the first thing, if I'm going to try anything, is take this emitter resistor for this fast transistor, run it off a rail that's 3 volts lower than the ground rail. The negative rail. See what that does first. Because if I have to widen both the input stage and fast rails in comparison to the output stage rails and driver rails, I'm going to have to produce 2 rails, not just 1 rail. So, yeah. Let's get that figured out. I'll turn the soldering iron on. I'll lift that resistor. I'll hook this onto it. What I've done, yeah, it's going to inject noise in the circuit. It's a switching supply. I've got, that's coming over here, negative, and the positive's going to the negative. So this can be set, you know, 3 volts. Oh, I've got to put the switch on the front of this thing. It's so stupid. I can set this at 3 volts, which it's already set at, 2.99 volts. 10 amps, there's no current limit on it. What I'll do is actually I'll set it for 2 amps. All good. Alright, so we've got our minus 3 volts. I'll just power the amp down before I unsolder stuff. The hell, I can't get this resistor up. God, I've lost my touch. My magic touch has disappeared in 9 days. This is why I hate leaving the lab. You forget what you're doing, you lose your touch, just... Alright, so now, Mr. Vast transistor's got 3 volts lower than the rail it was hooked up to. I'll turn this on again, see what happens. Starts up without a problem. See what that does to the offset. I mean, it shouldn't. The input stage should just correct for it. It's obviously going to require, it's going to eat into some of the swing to have to compensate for it, but no, it doesn't work at all. Jeez. Really? minus 3 volts lower just pegs straight to the negative rail. And is not trying to amplify at all. That's interesting. Can't say I was expecting that. Yeah, that's getting hot. I don't want to cook my nice, good transistors. It's not like real hot, but it was getting there. If you left it for 5 minutes, they might go pop or something like that. Okay. I wasn't expecting that. I really thought that was going to work. Let me just... No, that's right. Positive to negative. Negative below negative 3 volts. No, that's... Yeah, I hooked that up right. I was really hoping I could do something with the rail, because I really don't want... Like I said, I want all this stuff sort of isolated from the rails anyway. And I don't want to add the diode. I'll be honest. Anything that's a band-aid that ruins performance in my mind is not the correct fix. I'm the sort of person that will literally spend like just copious amounts of time finding the fix for something, just to get the right fix instead of putting a band-aid on it. I can see myself at the moment basically cutting out the whole VAS section and redesigning it as a full complementary VAS. I really have not been happy with Doug Self's blameless VAS, which, you know, it was claimed that it's designed to, you know, minimize loading of the input stage and reduce THD by so much and all that, but whilst it might do that, it has all these other flaws. Alright, so now I've got both the emitters of the beta enhanced transistor and the VAS transistor 3 volts below the rail. I'm going to power up again, see what happens. I don't know why I took the meter away. Moving too quick today, I'm just happy to be back. Alright, no excessive current draw, but again, pegged to the negative rail. Now, here's the interesting thing about this. Remember before, when we were rail sticking, we were sticking at the positive rail. With the VAS transistor just a little bit below, right? Just a little bit below the negative rail, all of a sudden we're sticking at the negative rail. That tells me that I'm somehow on the edge of teeter-tottering between going to the positive rail and going to the negative rail. That's what that tells me. I don't know if that makes sense to you guys or not, if you get what I'm trying to say, but something in here is sort of not sure which way it wants to go. Alright, we're going to have to, I don't know, start looking at this in a different light. Maybe I should start looking at voltages and try and work out what things are doing, i.e., you know, what voltage is on the base of the VAS transistor, what voltage is there when it's stuck at the rail, all that sort of stuff, and try and work out what's doing what. Maybe that will shed light into, you know, what the heck is going on. Sorry, I'm one of those people, all my solder joints have got to be nice and shiny and perfect. I'm a bit of a nerd like that. Alright, it's back to where it was. Let's have another look, see if we're back to where we should be in terms of offset. Yep. You'd think it's the best amp in the world looking at that. The way it starts up, it's just... This is what gets me so bloody annoyed. Alright, I'm going to try and give it bias. Don't forget, I've got the bias jumped over. Copious amounts of current and it sticks to the positive rail. Ah. What if now I try and run that? Let's try. Let me hook this up over the other side so I don't have to keep moving my meter. I keep moving it because I'm worried about burning the leads, but if I'm just a bit smarter. Yes. Let's try the sub rail again with bias. If anyone's got suggestions, please leave it in the comment section. I don't understand why no one leaves suggestions down there. And again, not if you're going to be a dick. I mean, if you genuinely just want to help. Because, I mean, the other day someone tried to lecture me on building transformers again. This has happened about 3 times now. And it's quite annoying. You know, like, fuck. If you see me do something wrong, tell me. I won't bite your head off for it. If I ask for help, help me. But for some reason, when I ask a question, no one replies. But when I make a video explaining how to do something, someone will write me a 2-paragraph lecture telling me how to do what I've just explained how to do. Don't know. Not saying it to you guys that are watching this video. I'm just saying that that's what I get out of the YouTube comment section a lot of the time. There are good commenters too, and you know who you are, and I love you guys because you are just genuine, down-to-earth people. But I guess you got to take the good with the bad. It's the way it is. I do get that too. Alright, well, let's just try just the VAS transistor. Still got my 3 volts on, so I'll turn the other power supplies on. Holy shit. I've never seen it pull that much current. That pulled the whole 2 amps. So that basically would have tried to go and turn both sides on all the way, I'd say, is what just tried to happen there. So shits and gigs. Not that the amp should need this to be stable, but I just want to short over my input. Just so that the capacitor there can build up the same base voltage and act as a bit of a buffer on the base of that input transistor, just like the feedback capacitor ground does, just to help stabilize the 2 sides. Have another quick look. Alright, 2 amps. Alright, I'll just do this like this, because we're going backwards and forwards. Connect that back to the 0 volt rail. Now it's at 1.1 amps, so kind of trying to regulate, but it still can't. When I turn it on with the bias open and the fast transistor on its own rail, is this LED coming on? Hold on. Oh, I can't get over quick enough. And I can't leave it powered up. There's got to be a way around this. Oh, what if I turn it around backwards? Oh, I've got to stretch over. Tongue at the right angle. That looks like it's dimmer, eh? And it certainly goes off as soon as the power supply is turned down. Okay. Look, like I said, I'm not for the Baker clamp. Certainly not my solution. Even if it has to be the solution, I will obviously use it for this amp and then go on to design another amp that addresses all these issues with a complementary fast stage and other things like that, you know, but just saying. All right. I'm going to get a diode. Actually, before I do that, I'm going to go get, say, 220 picofarad capacitor. I'm just going to tack it from the start of this feedback to the collector of the VAS transistor. Sort of just like a traditional millicap. I'll just go get one. Alright, 220 picofarad. Before I do that, I'm going to do two things. One, I have come across stud caps like a 220 that had like 13 picofarads in it. Obviously the roll was split and only part of the roll was connected to the you know what I'm trying to say. Alright, that's a 220. So, second thing I was thinking about, I highly doubt this, but let's just take one of these bias strings and take a power supply and take, what am I running through it roughly? I think it was 9 milliamps. Let's stick 9 milliamps across a bias string. I'll voltage limit it at, say, 5 volts, you know. Just so it doesn't go back into circuitry and reverse breakdown VB junctions and damage other crap. I just want to say, do I end up with the 4.2, 4.5, whatever bias spread of voltage? Or is one of my diodes open? Because the way it acts when I open the bias is like... Actually, no, because that resistor's in the middle of the diodes. Okay, diodes are fine. Alright, let's put the capacitor in. Didn't even have to test that, just had to think about it. Cool. So I'm going to, like I said, tack this across base of the... No, not the base, the... Hold on. Oh, that's the feedback cap. Yeah, base of beta enhanced transistor. And the other end of it to the collector of the VAS transistor. Alright. Going to try and power it up again with the bias open. But when I say open, I don't mean open all the way. I mean there's a resistor in the diode string that sets the bias at, you know, roughly 16 millivolts or whatever it's supposed to be. I can't remember. I think it was actually way lower. I can't remember anyway. And if you short that resistor, it'll have like no bias. That's what I mean when I say open and closing the bias. I'm not opening the diode string because obviously, yeah, it would be stuck both sides turned on. That's not what's going on for those that are wondering. I'm going to power up. No, 1.1 amp. Cool. I'm going to close the bias. Power up again. Yep, 27 milliamps. Holy shit. Hold on a second. I just smelt something, and the voltage I just saw there, that's not possible. Oh, I'm not on ground. I'm on one of the rails. Okay. I thought I was clipped onto the ground rail and the output. You gotta understand the output can only swing positive or negative. You can only have one of the two rails. You can't have Oh god, unless it's swinging, you can't have more than that. Alright, let's try again. $27 milliamps. Offset's gone away. Let's just see how stable it is. Ah! Well. I think we found our problem. And I tell you, I'm a happy man because, like I said, I did not want to put a Baker clamp in here. So it seems to be Miller related. So that's good. So I could bust the scope back out, turn the time base up. Maybe I just didn't have the time base turned up and it was a really high frequency, small oscillation. The other thing, it could have been buried in the noise and we just couldn't see it. But that's certainly what was happening. Yeah, I can't get that to misbehave at all now. Yeah, that's behaving like a normal amplifier. But I still can't open the bias. But it does stabilize when I close it again. Now that's odd. The plot thickens. Yeah, that's really stable now. Like, real stable. Okay, you know what I'm thinking? The 2-pole compensation, output inclusive. The cap values I chose. What did I choose? Because I remember my first build, I had put 470 and 47 picofarad. I'm pretty sure. And then I reduced it and I've put in, was it 68 and 150? No, 82 and 100, that's right. So we've got about 40 picofarads. Now we've got about 260 picofarads. But there's still something else going on here. Okay, well, you know what we could do? We could get silly. I'll just go get 100 nanofarad disc ceramic and I'll just tack it across here and we'll see if the bias will turn on then. $104 disc ceramic. Like I said, this is just stupid overcompensation, but it will answer the question. Right. So now it's stupidly overcompensated. Can I open the bias? No. Hold on. I can hear an oscillation in the heatsink, but I think it's the transistors. I just want to make sure it's not. No. God, this is bloody odd. Somehow that bias network is setting up some sort of oscillation, I think. I really think that's what's going on. I wouldn't be half surprised if I snipped these 2 wires and just put a pot in there and just dialed it in. Obviously the bias wouldn't be thermally compensated, but just dialed in a level that it would work. I have a really funny feeling. it looks like our VAS was undercompensated. The 100 nano hasn't done anything. The 220 has. Now, there was already 40 there. I've gone up to 220. So, let me go get 100 and stick 100 across there. That'd be about 140. I want to see at what point, you know, we keep our stability decreasing in this value. And then I can do some math on what the two values should be. And then we can put those values in and see how that works. That's what I'm going to do right now. I'm not going to even bother going any further with anything else because I've already discovered something. So why not address it, right? All right, I'll power this down. I just shorted the base to the collector of that transistor. That's why you saw that light flash. It wasn't a destructive short. Don't worry. All right, so 220. I might put. Let's see. I might even go 82 because there's 40 in there. With 82 across that, it's about 120. And I'm trying to see, you know, how low I can go. I don't want to do this in a million steps. I'd rather do it in 3 or 4 steps. Ideally, I could just get a variable capacitor and dial it in, but it's all right. All right, 80, oh, just bit my tongue. 82 picofarads in there. Wow. Really? That's cool. You know what? This is shedding light on something. It's starting to appear like adding just normal Miller compensation is fixing it. I'm starting to wonder if the two-pole compensation is actually a problem. Output inclusive two-pole compensation. Because I've drastically reduced this. I just put 82 picofarads across 40-ish. Tell you what. We've got that 2.2k voltage divider thing. Let's lift both of those resistors where they go to the Miller cap, one of them. So now we don't have our output connected to our Miller compensation midpoint, and we don't have our ground connected via the two 2.2k resistors. We just have the two caps in series across the same location as where I put that. Let's see if that's stable. So what I've done is I've removed the 2-pole and the output inclusion. No. Okay, so what have we learned? The out pole and the 2-pole inclusive compensation is not what's causing the problem. It's the values of the capacitors, and it's not that far off. When I was being conservative, I've obviously almost done okay. because adding 82 picofarad did fix it. I'm going to put these resistors back because other people have researched this topic. This does work, and as it's made no difference, I don't believe it's the cause of the problem at all, or even having an effect. So I'll put those back. Bit fiddly to try and get them in there, but I will. Just realised my camera is probably on the wrong angle. My apologies. I'll sort that out in a sec. But it does seem like there are two separate problems at play here, I have to admit. Alright, those resistors are back where I want them. I'm just going to flow a little bit of solder in there. Sorry again for the view, but I just need to get in on this angle. Alright, they're in there. So it seems like it wants about 100 picofarads of compensation. I'll give it 120 total. So now what I need to do is I need to calculate my two values. I'll go do that now and I'll be back. I won't bore you guys. What I'm going to do, I'm going to go watch my output inclusive 2-pole compensation video. Because in that video, it's just easy. I could bring up all the documents probably, but I've got to find them all. I'm going to have a quick browse through that. I know that having, which one is it? Sorry. The second capacitor, 1020 picofarad, smaller than the first one, corrects the mid-band peak. But I remember with different designs, like I think with output inclusive, you'd have, say, 1 to 5 to 1 to 10 times difference between the two, so like a 470 picofarad in series with a 47. With the 2-pole compensation where it just goes to ground, I think it was, so that's why I'm going to have a look at my video, because what I've come to realize is because this is a bit of both, the math might be a little bit different again, but I think that's just me forgetting something that was covered in that video. So I'm going to have a look at that video before I calculate these values, but I'm thinking around 220 picofarad caps. I need one to be a bit bigger. I've only got 270 and 220 at the moment. I've got two ways of doing this. I could use a 270 and a 220, or I could go and add, because I've got 22s, 10s, 47 picofarad ones as well. I could put the two 220s on there and just incrementally add 10 or 20 puff in parallel to it to get the value I need, whilst I wait for the correct value cap, which I'll have to order to arrive, you know. So I'll go do this now and I'll be back. Alright. Seeing as the ratio is changed, it seems quite a bit when it's done this way, and you only want a bit of a difference between the two. What I'm going to do is I'm going to put the 270 and the 220 in there. Calculate what the series capacitance is, effective millicapacitance. I'm going to work out what that bandwidth limiting is. I'm going to work out, oh no, it's my feedback. Sorry, I'm not thinking. Sorry, I'm really not thinking straight. I need to do some research. I need to work out, because the thing is, something I have heard time and time again is that you want your input to dominate the, how do I say this, bandwidth of the amplifier, not the feedback network. So I don't want to go and increase the values in the feedback network and only have the mere 100 picofarads on the input. Got a bit of thinking to do here, but yeah, I just thought I'd point that out before I go and delve into it any deeper, because I don't want to confuse people. But it's just, this is one of those areas where you sort of can't just change one thing without changing other things. So unfortunately, that's how it is. Alright, so I've done it again. Actually, I'm a bit confused here. Because it says, you know, the feedback and the input stage should have the most dominant pole, but my research also told me that the input stage should have the highest bandwidth. If the input stage has got the most dominant pole, wouldn't that mean that its RC is lower bandwidth than the feedback network? I'm a little bit confused. Alright, I've got this down pat. So, there's two things going on at play here, right? Well, more than two, but let's just focus on these two. We've got our low frequency cutoff, which is determined by the input capacitor and its resistance to ground, which on this amp, it's set at something ridiculous like 0.016 of a hertz or something like that. My feedback network, it's like 0.058 of a hertz. It's higher by, you know, not much, but yeah, times 5 or something like that. I can't remember. So that's fine. That's how that's supposed to be. The input should dominate it. The other thing would be your high frequency filter on the input, the little polystyrene cap and the what have I got across at 15k? Yeah, 15k. Oh yeah, well that's the resistor that goes to ground, of course. Sorry. That is 500 kilohertz roughly. So what I need to work out now is the Miller effect of the VAS stage. And the way you do that is by calculating the transconductance of the stage and doing some math with that and the capacitance, and that will tell you your bandwidth. Because what I need to work out is, you know, as I increase the capacitor value here on the Miller, I'm going to get to a point where this is going to start to dominate the input, and we don't want that. So that's at the point where we'd have to change that cap there and those two. So I'm going to go calculate that now, but at least I've got that clear for me, and I'm hoping it's clear for you guys. You know, it's the same thing with, I would imagine, the same thing for this little capacitor and resistor that goes across the feedback resistor. I'd imagine that too, which in my case is set at 500 kilohertz, should be around the same ballpark as the bandwidth limit of the input, because that's there to help with square wave response right up at the top end of the spectrum. So that's why I went for those values. So I hope that all makes sense. That being said, I know what values I need here, you know, like a couple of 220s with an extra 22 picofarads on one of them, or I could use a 270 and a 220. You know what, that's 30, 40, 50, 60. It's only 50 extra picofarads. It might be a little bit, but we'll see. I'll try that. But I have to work out the bandwidth limit of that. So, and I'm terrible at math. So I've got to work out all the different calculations you do, the current source, the current that's setting the gain on this stage. I've got to calculate that with this Miller cap formula, and then I can come back and work out what the bandwidth is. So we're going to go do that now. I just hope I've explained that in a way that's made sense as to why that has to be, because the input stage needs to dominate, essentially, how do I say this in layman terms? It needs to dominate the overall control of the bandwidth and frequency response of the amplifier. You don't want the input stage to be less dominant and controlling, and the feedback stage to be limiting, if that makes sense. Alright, I'll be back momentarily. Alright, my maths is poor, but I've managed to work out with the level of gain that I've got, 100 picofarads isn't going to limit the bandwidth by jack shit compared to the input bandwidth limiting. It's all through the roof. So I'm going to fit two 220s. I've got these 270s, but I'll just give you guys a look at them. This is really funny. When I order these polystyrene capacitors, they always send me some random capacitors for free. And it's always like just 2 random capacitors. And I got these. I'll show you. And you're probably going, okay, well, what's wrong with them? Let's have a look in the ends. What? I mean, they literally look like the ends are all shredded up and the alloy is touching the leads. I've never seen anything like that. You know what's odd? Get the LCR meter, analyze them. .270 picofarad. Bang on, like there's some sort of high quality cap. I don't know what to make of them. It could be a bit of like a illusion. It could be the plastic and polystyrene in there and the metal is sort of like glistening through it and it's just plastic that's in there. I don't know what to make of that. I guess I could test it. I don't feel like doing this now anyway. They look dodgy as hell. What I'm going to do is put 2 220s in there. When it comes to analysis, I can, like I said, just tack an extra 10 picofarad, 22 picofarad, 47, would probably be 22, across the one that's supposed to be the larger value, which is what, the first one? Yeah, the second one's 82 picofarads, the first one's 100, so I'll put the 2 220s in there. Oh, sorry, that's an 82. I'll put the 2 220s in there. And when it comes to fine tuning day, I'll just tack the extra 22 or whatever it is picofarads across it. So I'll get that done now, and then we'll come back and see what the other problem is that it's got that's related to stability. Alright, so I've got the two 220 picofarad millicaps in there. Still output inclusive 2-pole compensation. Like I showed a minute ago, it didn't matter removing both and just having just plain Miller cap across it. It made no difference. It was the actual value of the combined capacitance that stabilized it. So I've left the output inclusive 2-pole compensation there. So we've got 2 220s in there for now. Let's power it up and verify that it's more stable. All right. That's what I like to see. That's me directly touching the input, literally on the base side. I'll touch the base. Yeah, okay, so that's stable. I'll touch the base on the feedback side too. Yeah, so we're happy with that. I'm happy with that. Should stop hitting that capacitor and bending it. Anyway, that's good. However, if I open BIOS, yeah, no, 1.2 amp draw. As soon as I close it, however, it does stabilize and stop drawing current. So it seems that we've solved one problem. Where it appears that there was two issues going on here, it appears, where it appeared that there was one issue going on here, it actually seems that there was two. We solved one. So that's good. So I'm really fussy with cable routing. I want everything to be neat. And as far away from surrounding components and everything as possible. Anyway, alright, so I still need to work out why I can't bias it. What does it do when I try and bias it? Okay, it still sits in the middle. What happens to the current source? Okay, that goes dim. So let's think about this for a moment. For that to go dim, this is really odd. For that to go dim, the VAS transistor can't be on. I mean, because if it's on, or saturated or whatever, we should be sinking current. Let's try the sub-rail thing again. I think I'm going to end the video pretty soon because it's already gone on for quite some time. I started this video like 9-10 days ago, as you know, and I've just worked out back where I'm up to today, and I've already covered a little bit today, so I don't want it to get too confusing for me or for you guys. Let's try the -3 volts on the, I don't know why I don't just grab something I can actually lift with. I don't think sometimes. I've got the tools to do everything perfectly, but I always grab stupid tools and do a shit job. Human nature, I swear. Alright, well that's 3 volts below everything else. The only problem with this is it's going to start up with an additional 3 volt offset bias, whatever you want to think of it, here, because the rest of the rails come up when I turn the supplies on. I can't turn all 3 on at the same time. You know what I can do? I can put a shorting link across the 3 volt supply. I can leave it on or turn it off. It's current limited. And turn the other 2 supplies on and then take the shorting link out. I can do that. Let's do that. Let's do that because that gives us a little bit of insight into what it looks like going the other way, if that makes sense. Like, instead of starting up with the 3 volt rail already there, we're starting up with the normal rails and then adding the 3 volt rail after startup. So I'll just short this. Like I said, this supplies current limited, so it's just pumping 2 amps into a piece of wire at 150 millivolts. So now I turn the other 2 supplies on. Hey, won't start up. Oh, wait. We should have our rail here. Hold on. Okay, that was just probably a bit of inductance in this extra bit of wire. I'm now going to remove the shorting link and see what happens to the supplies. Okay, so I've removed the shorting link. That was probably the resistor getting hot just from what I did before then. Okay, so we're now running. We've got our minus 3 volts on the VAS transistor. That's interesting. House stability. Okay. Interesting. I wonder if I can bias it. Oh, geez. No, that's certainly not working. That's making that transistor just absolutely sink current to drive this. Let me put this back down to the rail. I know that won't be damaged yet. It's not that hot, but I'm not going to leave it like that either. Could try running this entire negative rail. The bottom of the input stage, the bottom of the beta enhance, and the bottom of the VAS transistor all off of a sub rail. That's something else I could do. I can lift this resistor here on this end and attach it there, 22 ohm power rail resistor to my sub rail. I can try that. Out of curiosity, now that we've fixed one problem without band-aiding anything, the instability was improper Miller compensation. That's resolved. I've increased the capacitor value to something stupid to make sure that this is fully compensated and there was no increase in effect beyond a certain value. So I'm confident on that. Let's clip on to the collector of the VAS transistor. Let's clip on to the base of the beta enhanced transistor, and I've got everything ready. I've organized all my SMD components. I've ordered the BAS21Js, so I've got all the different diodes, all the BAV, BAS series, right up to the BAS21J. I've got all your normal stuff too. I'm just going to go grab like a 5711 or something like that for now. I want to see what the Baker clamp does, because like I said, I don't want to add the Baker clamp as the fix, but let's see if that now resolves the second problem, and if it does, well then we just got to come up with a solution for that, to not use a Baker clamp. Alright, I'm just going to have a quick gaze at... Was that not plugged in? Hold on a sec. You know when I just ran it off the sub rail and I thought it was okay, but that was hot? I don't think I had my ground hooked up, so it was probably at the rail. Alright, anyway, let's just see what the forward voltage drop is roughly at, I think, a milliamp it's going to be. Yeah, that's what I was expecting. That seems like a good starting ground for this. I honestly think that it's way too low, but I mean, it's going to tell us if this is what's happening. Now let me just verify which way this goes. Hold on, one sec. So pointing, okay, I'm going to have to look, because I've got Baker clamps installed. I've got a few different diagrams I've looked at where people have done this, and I've seen it in a few different locations. I also don't know what diodes people are using. For example, I'm looking at one here where there's a BAV21. I'm not even sure if that's a Schottky or a normal diode. I'm going to have to pause the video and have a look. But it's just across the base to collector of the VAS transistor. It's not across both of them. And I'm not too sure that if I was to go across both of them, my worry is, like I said before, the voltage drop being lower than the two transistors. It's not going to just stop it from going into saturation. It's going to barely stop it from, almost stop it from doing anything. That's the way I see it anyway. Let me just have a look at a few things. Alright, so I'm looking at another one, that the one I showed you guys with the complementary VAS. It's like the same as my amplifier, same as my amp, basically different input stage, but basically same VAS, just full complementary with no current sources, sinks. And as you can see, you've got your Miller cap, your Beta Enhance, your VAS, and the Bass 21 HM in this case, going from the base to the collector. So let's do that. So we're going to point it going at the collector, and it's going to go from the base. Going to hook my meter back up so that we can see what's actually going on. I will remember to hook up the ground this time. I don't know why I didn't hook it up over here. I've got ground right here for the bloody Zabler network. How did I not think of that? God. Alright. I was just looking at those black wires, making sure they actually went back to ground, not negative. Yeah, they do. All good. Alright, I'm going to power up and we'll see what this does. Alright, well, the amplifier has started up. Still seems stable. It actually seems a little bit more responsive now. That's hilarious. No. As you can see, as soon as I open bias, well, there you go, 47 volts. So that kind of tells you what the transistors are doing. The positive side, the NPN side's turned on about 3/4, and the other side's turned on about 1/4, I think. And you're seeing offset and a lot of current getting drawn. Blimey, why? Why is it so? Alright, I'm going to remove the Baker clamp because, and I'm bloody happy that that didn't make a difference too, because I didn't want it to. Let's investigate other things. Is our bias voltage doing strange things? Let's have a look at that. So I'm going to go across the bases of, well, I'm going to go across the input stage and bias string end of the two resistors that go to the bases of the driver transistors. And with the bias resistor shorted over, we've got 2.877 volts, which is obviously way under biased. Triple Darlington should be about 4.5 volts, I think. Anyway, with bias, that's interesting because I would think, yeah, 3.5 to 4.5 volts would be in the range. 4.5 probably is quite a bit. Well, it depends how much bias current you're running. But that's quite interesting. There's nothing funny about the bias voltage there. There's nothing remotely funny about that. Okay, so now I'm starting to wonder about another theory. Are we literally, because there was obviously some very high frequency oscillation going on before here that these Miller caps have fixed, the 220s. Maybe when I was trying to bias it before, the resistor values I calculated just completely wrong. And again, we weren't really biasing it, but we were biasing it and it was oscillating. And we were looking at the current across the emitter resistors of combined oscillation power and bias. What I'm getting at is basically when I open that resistor, it tries to apply too much bias because the resistor value is incorrect. Let's see if that theory is true. And that's going to be easy to prove because with it closed, there's no bias. So if I just put a pot across it and slowly open the pot up from fully short, that's where the other resistor went. I've been looking for this. That's hilarious. I literally put another 5.6k resistor here because the metal film one disappeared and it was in the solder tray. Anyways, I'm going to go get a pot. One moment, please. Highly recommend you guys do this. Ever since I started prototyping on breadboard, literally, and I've needed to plug a pot, you'll notice most of these pots the wires aren't tinned on the end, it's just copper, because I'll just solder 3 wires onto a pot and you can put it in your breadboard and tune stuff in, you know. And I've got a whole host of different things that I've used over the years with breadboard circuit designs, right? And I keep it all in this box. There's even a bloody selector switch in here with a few wires hooked up to it. You know, a multi-turn pot, a switch. There's some random crap in here. You know, 2 pots on one board, again, to stick into a breadboard. This crap is so handy when you're designing stuff that when I was finished, instead of removing all the wires and putting the pots back in the box, I've kept all this in this box, and every time I'm designing stuff, I go back to this box and it's just ready. I just wanted to show you guys that and say, you know, food for thought. It's a bloody good idea. It works. Like right now, I want a pot that's fairly low in value, like 1k, 500 ohms, something like that. That'll do, 1k. Just grab it out. It's ready to go, you know. What I'll do is I'll wind this all the way to the end it's turned to. And I'll take some alligator clips and I'll just clip on, in this case, I might clip onto here. Clip onto the pot, and then I'll put this onto the bias resistor in parallel with it. So we'll have no bias when I take the shorting link off. I'll just put the phone the other way so you guys can kind of see. Hold on, my phone's going to fall. Alright, just had to make a small modification. Now I can actually just... That's wonderful for you guys. Alright, so now you can see what I'm doing here. I've put the pot across that resistor and I'm going to take the shorting link off. So it's still no bias right now, but what I can do is I can apply bias slowly whilst seeing what the amp does, and if it goes crazy, I've just got to turn the pot back the other way. It's probably a good idea, and I'll put this up here. Oh, it's close enough. You guys can see the 2 current sources. There's nothing else that's going to give you a visual indication of what the board's doing, so you can kind of see everything you need to see. I'll try and get my arms around here. And okay, I'm actually able to get bias. You've got to be kidding me. And I know that because I'm looking at my power supply. So I'm going to move the phone back here. I'm going to change the location of this to emitter resistors. This is hilarious. Because the first time, if you guys remember, when I first put this thing together, I went to bias it. I thought I was biasing it. And then I realized it was oscillating. And, you know, some of the current we were looking at was oscillation, not bias. And so the bias resistors changed value. And it's happened again. See, this is the thing. I'm not trying to be a cocky prick here, but it really pays to pick up on these things because, you know, if I didn't pick up on it, I could have spent another month doing the same thing before realizing what's going on. It's quite interesting how one problem can present itself in such a strange way. So we don't have any AC across the resistor. There's no bias now anyway. Anyway, I'm going to slowly turn this up, and as you can see, I can bias it now. I've got janky ass connections here. I'm going to have to solder something But I just want to see what's going on. I mean, holy cow, I think the amplifier's finally working. I think we've actually solved both the problems in the one video. Finally. And those current sources look happy. That's coming back up like I'd expect it to. It will try and suddenly warm up, and then as the heatsink warms up, the diodes will warm up, and then it will sort of come back down again, and it will just even out. That's if there's no oscillation there and just my BIOS network is doing its thing. But this is good because this actually answers a lot of questions, because I from the beginning, I mean, you guys know how much effort I've put into stiffening the rails up. What do you call it? Bypassing the rails, bulk storage and RC stuff and all that sort of stuff, clipping diodes, my wiring, very stout. So this is why from the get-go I had a hard time believing that the VAS transistor had some problem because of the rail. But that's what everyone says. I guess that's what other people are having problems with, probably because they're not too good at layout. And there you go, you see it's coming back down already. Finally we had BIOS. Oh my god, that took how long? I can't believe it. I can finally set BIOS. You see it's working. It's warmed up and it started tracking. So I just bumped. Terribly loose connection here. My apologies. This is... Let me just turn this off. I'm just going to solder the pot over it. Work out what the resistance needs to be. I'll just get rid of this 680 ohm resistor. Alright, there's only about 9 milliamps going through this string, so the pot's not going to get smoked if I go to the end of the track. Those of you that do electronics know what I'm talking about. Oh god. For those of you that don't know, us people that build circuits, we use this trick a lot to dial in a resistance without doing math, where you use a pot. And that's all well and fine and dandy, it's all well and good, but every so often you've got a bit too much current flowing and you accidentally bottom the pot out. And what happens is you've got just a little bit of track left and it can't dissipate the power and it goes poof and blows open. Anyway. Oh yes, I'll turn the pot all the way down. Yep, okay. Apply power, no bias, and I will slowly wind up the pot. Wrong way. And that's a lot more smooth. Right, now, next problem I've, got. I don't know what my bias is supposed to be, and I know I calculated it and wrote it down somewhere, and if I have to go back and watch my videos, I'm not going to be happy. I'm sure it's in this book. If not, it's on the notes on the desk. I mean, we're waiting for this to track anyway, so I'm not wasting time here. 16 millivolts across. That seems excessive. 16? I thought it was something really small it worked out to be. You know what? I've got my calculator up on the computer here. Why am I trying to guess this? I wanted to run... I think I wanted to run about 30 milliamps. God, I can't remember. Ah, that's so annoying. I'm going to have to go back into my previous videos. Heatsink's not even warming up yet, so... no hot transistors. Actually that VAS transistor is going to need to be heat sunk. I had a feeling that that would end up getting as hot as this once it was running, because they're both going to be roughly at the same position. If you get what I'm saying. They're going to both dissipate the same power just sitting there idling, and when it's swinging, same thing again. The driver transistors are doing great. That's because of all the current gain we've got with the, the pre-drivers with the drivers. So that's good, because I didn't want to have to put too many more heat sinks in here. So it looks like we're going to have 4 riser boards, one there, and the same heat sink on each. That's great. I'm just going to turn this back down. Actually, it looks like it's just caught itself. It is slowing down, but I don't need it that high. Let me go work out a good value. I'll be back soon. I'm going to set it around 5.5 millivolts. That's going to be about 25 milliamps of bias per device, per transistor. Oops. Alright, what I'm going to do is I'm going to let it, come to an equilibrium temperature-wise. And then I will work out the value. How much play does the pot still have with our new resistor value? Oh, plenty. That's wonderful. Okay, that's what I wanted. Good, I don't have to adjust that. Yay! I wouldn't imagine it's drifted from 680 ohms too much. It's probably, I don't know, gone down by half or something. You'd be surprised. Alright, like I said, I'm going to get this to stabilize, but I'm not going to put too much effort into it. I'm just going to get it to stabilize and then measure the resistor value and fit the resistor. Reason for this, remember, if I cool this heatsink down, that number will drop. If it gets hotter, it's going to increase. I need to thermally couple that LED to that heatsink. That will solve that problem. The temp code of that LED and that transistor is very close. Not perfect, but it's one's negative and one's positive, and they even out quite nicely. So my solution is to basically jam the LED with some glue or something in the heatsink here. I might get the grinder and, well, I'll flatten 2 sides of the LED a little bit so that it actually has a bit of flat contact area to the fin that's either side of it, and I'll glue it in there so it's got good thermal contact. And then I'll actually worry about setting the bias, because at the moment, and to tell you the truth, I need to build a riser board for this transistor and heatsink that too, because when it's heat sunk, it's going to be running cooler, and that's also going to throw the bias off. I'm sure it will. I haven't tested that theory, but I mean, let's just give it a cold shot. Oh yeah, you know why? Because that's inside the feedback loop. Yeah, okay. The input stage just drives that harder or less harder to compensate. All right, so it's just this. I need to worry about getting the LED on there, and then we've got a really stable amp. I mean, look at the bias. I am so pleased. I'm going to end this video here, because it's probably like a 2-hour video already or something, and I don't want to bore you guys. We've already solved the 2... I'm just going to leave it where it is for now. I'll leave it there. We've already solved the 2 major problems that this thing had. I think that's good enough for one video without a Baker clamp. This is wonderful, because now, providing it's got gain and it's actually working as an amplifier, what I can do then is I can start investigating adding current sources and sinks to this fast stage like I said I wanted to, or at least a regulated rail or something. Like I said, I want rejection from the rails. So that's good. We're finally moving forward with the design process. Didn't have to put a Baker clamp in there. Like I said, I don't like band-aiding things. So yeah, I think that bias is more than stable. What do you guys think? Heat sinks, like, you know, not even lukewarm. And the diodes are tracking wonderfully already. I'm a very happy man. Alright. I may sort this LED out off video. I'm not too sure. I might do it in the next video. Alright. Very important update before the end of the video. I've just realised something. This is definitely going to be an issue. What's this, a 3790? Is that the NPN? Yes. Alright. Now, some of you might already know where I'm about to go with this, but when I was trying to get the VAS to work, I increased the current on the VAS stage. Now, I didn't do this because it needed more current for more gain or anything like that. This was all DC characteristics. However, I'm running what, 10, 12 milliamps. Jesus. Oh. Sometimes I don't think. I have no pot across. Oh my god. Let's just fix that problem up quickly. Alright. My bias. Uh, 8 milliamps. Really? 8 milliamps? Is that what I ended up setting it at? Really? Ah, that's quite interesting. I thought I had it up at 12. I must have turned it up and back down. Okay. I'm not so concerned about that. And here's why. Let me just turn the power supplies back off. I know what my resistor value is, by the way. It's 91 ohms. Now, as we all know, beta changes with current, and depending on the transistor, that changes. This is an NPN. Oops. At 10 microamps, it's got a gain of about 100. At 1 milliamp, it's got a gain what? I thought it was higher at 1 milliamp when I tested another one. So let me just go get my drawer of these. I told you I stocked up on these. Once I realised how good these transistors were. Yeah, some of them go higher at 1 milliamp. Oh, you know what? My transistor test is going dinky. I need to work on the switch. Anyway, the point I'm getting at is at 10 milliamps, they've got a gain of about 30, and I've tested this one as well. It's the same thing. Anyway, we'll sort this out in another video. Like gold electroplate contacts or something, I don't know. Anyhow, that's at 10 milliamps. Obviously, as that current drops off, the gain starts to go back towards the 100 end. So I don't want too much current going through here. I think 6 milliamps is what I would rather run. Here's the thing. The annoying thing is every time I change the current source, the bias resistor's got to change. So what I think we should do is actually sort out that first. Now, I'm not going to do it in this video, but I just wanted to explain this, just so if anyone was wondering or hadn't thought of this, it's in your mind now, for those playing along at home. But in the next video, that's what I'm going to do. I'm going to see how much gain we've got, see if the amp's actually producing enough gain. Do I need 8 milliamps? Can I turn it back down to 6? I don't even remember if I needed a heatsink at 6 milliamps. You know, so we might even be able to get away with getting rid of the riser board and the heatsink, which would be wonderful. We'll just have to see what we can do. So anyway, I'm going to leave off here for this video, and we'll continue on this subject in the next video. Alright, thanks for watching everybody, and I'll see you all soon. Bye.